Hello everyone again. Thank you for attending. We're going to talk about some electricity and magnetism non-calculus treatment, though I'm going to show you a calculus treatment of something interesting for those of you that have the calculus background. I'll probably use that same treatment in the calculus treatment of electricity and magnetism when that's used in calculus-based electricity and magnetism. You don't have to know the calculus treatment that I'm about to show you regarding the electric field that is present above an infinitely long and infinitely wide sheet of charge. And we're associating this with how much, what's going on in that regard. So let me kind of say a couple things about that. They say something, and I'm going to kind of hook this around a little bit, you guys. You can say this in a lot of ways, but for our purposes, if it is, in the Serway book, they say something, a non-conducting plane sheet of charge, the charges are there, however much is there. Can we say something? Can we say how much of an E field is present on a non-conducting plane sheet of charge? The plane is very, very big. How big? Well, for all practical purposes, for everything involved, we could say it's infinitely long and infinitely wide. Infinitely long and infinitely wide. So a non-conducting plane sheet of charge, we're going to say a couple things about it. Let's get to that in 1 second. What book are we talking about? Obviously, for those of you in any class that I'm teaching regarding this particular subject matter, and as long as we have this book, it is the book written by Serway and Vuille. It's College Physics, Volume 2, 11th edition. We're going to talk about Chapter 15, pages 521 to 526. There's 18 problems here, I think. Let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Of the 18, I'm going to do 10 on film right now, but the other 8, and all 18 for that matter, are going to scroll at the end of this video. The end of this video, all of the solutions, all 18 of these solutions are going to be present for you, so you can look at them that way. In addition, for those of you who have me as a teacher, in our Canvas account, we have access to this as well, as far as the hard copy of it. So more or less, the hard copy is going to scroll at the end of the video. Now, I said a couple things, you guys. Let me just kind of see here exactly where we're going to look. Yeah, okay, that sounds good enough to me. This is a very long sheet of charge. It's a non-conducting surface, so there's nothing, for our purposes, this is how we're going to look at it. The charges are more or less static. They're there. They're uniformly distributed. Let's assume they're all positive charges that are there. It's a charged sheet, non-conducting sheet. We'll say that all the charges under consideration are positive. They could just as easily all be negative as well, and the magnitudes would be right. We would just have to resolve things in terms of vectors a little differently. If these are all positive charges right here, and this is a positive test charge, the positive test charge would want to fire this way because of a differential element of positive charge here. Positive charge here, positive charge there. This differential element would want to push this positive test charge that way. Yeah, I know, but there's another differential element of charge just like that right over here, and it would want to push it this way. There's one right here coming out that way that'll push it into the board. There's another one opposite that'll push it out of the board. This will be like a cone of all these pushes happening here, and all horizontal components cancel out. So you'd have another charge, like we said, you have a differential element of charge here, And it would be, as we said, we have this, and this guy would be pushing this way. You got this here, you got this there, and these cancel. They'd be canceling all over the place. The thing that really matters is it's going to be going straight up from all that we see. In fact, you can make that little differential element of charge. I haven't drawn this that well, guys. Sorry about that. Put it right here. Maybe that's a little better to look at. Et cetera, et cetera. Yeah, I know, but I could go here and start playing with triangles here. I'd go closer and start playing with triangles. I'd go far away and start playing with triangles. Yeah, but that entire cone of pushing, I guess you say, everything, everywhere cancels out regarding horizontal direction. But the vertical direction, all vertical components add up, and the E field is this way. All right, we already proved something in that regard. Is that the same way it would be if it was a conducting surface? Yeah, there's other considerations for the conducting surface. The total amount of charge that is there would split itself to top and bottom. Half would be on top, half would be on the bottom, and we'd have to kind of look at it that way. But that's another element in its own right. So they're not really going there, guys. I'm trying to look right here. Yeah, I mean, the way they have it set up is this would be, these are all positive charges, and they're going this way, they're going that way. If it were a conductor, you'd have positives at the edge, at the lower edge, and positives at the upper edge. But that's its own very interesting matter in that regard. So how would you actually do that? It wouldn't be a real significant difference. There's ways we could figure that out. But for right now, let's look at something that's pretty profound. We're not looking at, a lot of the mathematics would be very, very similar. So that's nothing to worry about. Let's keep it non-conducting surface, and let's talk about it. Well, we'd have a whole cone of pushing stuff, and all horizontal components cancel out. All of these cancel out, and it's all just a vertical. Okay. Same thing would be happening in some sense regarding that. I mean, you're saying, okay, how would you say that? How would you look at it? How would it work? Well, this guy right here, this red thing we drew here, kind of, it's a radius r away here, and it's a radius r away over there. So r here, and okay, and it circles around. So this ring of charge, in a sense, this ring of charge is contributing to what's going on here with the cone of all this pushing going on here. All of these cancel, and this is the guy that counts, as we said. Everywhere, no matter where you go. Well, to look at this, the differential element here, highlighted in red, the differential element of area is 2 pi r times dr. And that'll give you a differential. That's like, it's 2 pi r, the circle, and you just say, okay, that circumference isn't going to change tremendously compared to other considerations that we have going on. So I'm going to say 2 pi r, it's like you were taking the length of something, 2 pi r, and multiplying it by a width of dr, and you'd get an area. Well, that's kind of how this is, but that 2 pi r times dr, the length times the width, you're actually bending it into a circle of circumference, oddly enough, 2 pi r, and then the dr. Well, okay, not saying that's exact, but it's close enough, and it works quite good. What is the differential element of charge that is associated with that? Sigma is charge per unit area. Charge per unit area times a differential amount of area will give you the differential amount of charge that is pushing all the way around. Well, man, that's true, but in a sense, there's a differential of a differential. There's like, this is just a part of the dq. It isn't all the dq. There's a dq here, there's a dq here, there's a dq if you come out a bit, a dq here, a dq here, a dq, dq, and then all the way around, for all the way around, that's the all the way around thing is the dq. But a little piece of that dq, and this is just a little piece of the dq. This is a little piece of the dq. Down here is a little piece of the dq. Over on the other side is a little piece of the dq. The whole thing all the way around is the dq. So you got to be careful. Wait, we're not going to worry about that. Because there's so much symmetry and all the horizontal components cancel out, only the vertical contribution of each tiny element of the differential element of charge. There's a small amount of charge, and within that small amount of charge is composed of infinitely many small amounts of charge, I guess you could say. Well, all of them push this way. They push this way or that way, or into the board or out of the board, or it's this way or that way, or doesn't matter. All the horizontal components cancel. You can, and we know the length that's involved, the square root of the quantity a squared plus r squared. The square root of the quantity a squared plus r squared, using the Pythagorean formula. This is height a, this is length r. This right here, not an issue. It's always going to be the square root of the quantity a squared plus r squared, regardless of where you are. Are you here? Are you there? Are you over here, rather? Or there, or here, or over there, or over here. Doesn't matter. The square root of the quantity a squared, the square root of the quantity a squared plus r squared is the length for all of them. The small amount of charge that's there is the same for all of them. And if you add all those so if you were to take that and just sum all the vertical components, you might as well, if you're summing all the vertical components associated with really, really small amount of charge, just have dq, the ring element, comprise all the charge within that small ring right here. Well, how are you going to find this? Well, we already concluded everybody's canceling except for what's going upward. You're going to sum all the DEs, which are really DEYs. I mean, they're going to be just in the horizontal, just in the vertical direction that's going to matter. And we said, I'll tell you what, didn't we say that in general? They're going to say also in the book, of course, when they say this. As a general rule, E is KQ over some R squared. Well, true, and K is 1 over 4 pi epsilon naught. K is 1 over 4 pi epsilon naught. Q over R squared. Now R, here this is the R. It's a little more complicated. The R is the square root of the quantity a squared plus r squared. The square root of the quantity a squared plus r squared is a squared plus r squared. And that's your r squared, so to speak. That's your capital R squared, if you want to call it that. Maybe it'd be easier if I put a capital R here, I wouldn't confuse it with this. But you get the point, guys. The capital R in this case is the same as putting a small r there. That's just a linguistic issue, guys. Hopefully we're not going to get too hung up with that. But we're getting answers like this. If you're talking about one charge, what does one charge do? How does it do it? What happens? Okay. That's a big point here. Well, let me kind of do the summation of all the differential elements. The summation of all the differential elements is called an integral. Many of you in the non-calc based physics have had calculus. That's great. Use it. Use this. Listen to this. Hopefully it helps you out a little bit. If not, you'll see it in the future. Perhaps. If not, don't worry about it too much. I'm not going to, this is just something to show you that in the book they kind of show you to get away from calculus, they use Gauss's brilliant formula. Much of what the great mathematician Gauss had done to kind of derive this stuff. It's good. It's absolutely good. But can we do it? I mean, just quickly, let me just knock it out with some calculus, if you don't mind. E is equal to some integral of what? Now, here's where we got to watch out. The element that comes out this way, you guys, when we're doing something like this, and let me kind of, we spent a lot of time, like, kind of an end result of what's going to happen here, guys. So it's straight up from all of this thing going all the way to infinity lengthwise and going all the way to infinity widthwise. Everybody's going to cancel except for the vertical components. And at that point, no matter where you are on this infinite sheet, the E field is only vertically directed. All right, now the thing that works here, the thing that we do here, is just take one shot of this thing. It goes right here. If this is theta and this is 90 and this is 90 minus theta right here, and this is the up portion, let's say, for just one element of an element. This is one element, but man, we could take an element of that small element in our discussion and another element of that small element. And these guys, bam, come out, they hit, their horizontal components cancel out, and their vertical components add up. Same thing here. They're horizontal, they come out, bam, they hit, their horizontal components always, everywhere, are going to be canceling out. All the horizontal components are going to be canceling out, but the vertical components add up together. Now, how do they add up? Well, let's look at one of these differentials of a differential. This is the differential charge associated with this differential area. All of this in red and then covered by the white markings here. All of that is the dq. Yeah, there's almost like a small dq right here, a small dq right here, a small dq right here, a small dq right here. You add all the small dq's, you got the big dq. D small q, D small q, D small q, D small q. And here, you put them all together, you get D big Q. Okay, not the most mathematically rigorous way to conduct a discussion regarding that, but I'm just trying to give you an idea of what's happening here. All of this, though, is the sum of all of these even smaller elements and what they do. There's all this cancellation regarding regarding the horizontal projections, regarding the horizontal components. All of those horizontal components cancel out, and then so if the charge is here, if there's a point charge right here, oh, bam, something there, oh, horizontal components cancel, only the vertical component, and that happens with all that stuff right there. Well, with that in mind, if this is theta and this is 90 and this is 90 minus theta, vertical angles are congruent. This is 90 minus theta, that's also 90 minus theta. That's 90 minus theta, this is 90, there's theta again. Well, I'll tell you what, I care about, if this is E, if this guy right here is E, I care about the sine of theta times E. If this is E, this is E sine theta. Well, wait a minute, what's E sine theta? Isn't that the same as this triangle's leg right here and the hypotenuse right here divided in the right way? Meaning the opposite divided by the hypotenuse. So opposite divided by hypotenuse as R is being changed. Remember now, the R is right here. This thing could be a lot, it could be a lot smaller. The R could be a lot shorter. The R can go to 0 length, and the R can go to infinite length. R can go from R equals 0 to R goes to infinity. And in fact, we're going to make it do just that, because we're doing an infinitely long sheet, an infinitely big sheet, or at least close to an infinitely big sheet. Let's put it that way, if you allow that kind of ambiguity in the language, you guys. So what we're doing is, isn't it true that K times Q over R squared is the E field? K, which is 1 over 4 pi epsilon naught, times Q over R squared, This is the length of the hypotenuse squared. I guess it is the r squared. 1 over 4 pi epsilon naught is k. Here's a q, dq to be exact, and here's an r squared, times the sine of the angle between them. The sine of theta, ladies and gentlemen, is this ratio, this length, this size, divided by this size. This size divided by that size. This leg divided by the hypotenuse. This leg divided by the hypotenuse is still the sine of theta. Sounds good to me. The sine of theta times 1 over 4 pi epsilon naught dq over the hypotenuse squared, because this is the length, this is where the differential element of the differential element, right? I mean, the differential of the differential, if you allow me to say it. This to here is the square root of the sum, a squared plus r squared. A over the square root of the quantity, a squared plus r squared, is the sign in all instances. That's going to change. A is a constant, but r is going to keep changing. R is going to go from 0 to infinity. This is going to be a squared plus r squared, the square root of the quantity a squared plus r squared squared, which is just a squared plus r squared. dq on top of that, kq over r squared times the sine of theta. Sounds good to me. Let's integrate. Let's vary r. R is going to vary from a radius of 0 to a radius of infinity. 1 over 4 pi epsilon naught. I put this guy right here, which is the same as, you could say a lot of things about it. It's the square root of the quantity a squared plus r squared squared. It's the square root of the quantity a squared plus r squared squared. That's 2 over 2. That's to the 2 over 2 power. It's to the 1 power. This right here is to the 1/2 power. The same quantity multiplied with, a quantity to the 1/2 power times the same quantity to the 2 over 2 power. This quantity to the 2 over 2 power times this quantity to the 1/2 power is the quantity under consideration to the 3/2 power. What's this dq? Didn't we say we had to find the differential element of area, which is 2 pi r dr? And sigma times a, the bottom line is sigma over a, forgive me, no, is, got all the erasers, guys, and I'm not using them. Hold all the erasers I can, I guess, right? So let's see what we got. Sigma is q over a. It's uniformly distributed, so dq over dA is sigma. dq is sigma dA. dq is sigma dA. That's dA. We said dA was this, so sigma dA will give us that. So dq was sigma. So here's your dq. dq is sigma dA, which is this. The a was right here. We took this quantity, the quantity a squared plus r squared to the 1/2 power, times the quantity a squared plus r squared to the 1 power. When you multiply these two quantities, they're the same base. A squared plus r squared, the quantity to the 2 over 2, is a squared plus r squared to the 1 power. And this is the quantity a squared plus r squared to the 1/2 power. Common base, add the exponents, you get this. Bring the a, the a was here. You got these two together. Bring the a over here. The dq is this. And now you want to do that integral right there. You want to do that integral right there, you guys. So, and there's a lot that can happen here to make this happen, I guess you could say. So let me just say really quickly, again, you guys, this is, I'm directing this toward a non-calc based class, but many of you already have the calculus background, so I think this is good exercise for us to look at. If those of you are going to be having the calculus later on, also good to know. If not, don't worry about it. We can look at the other stuff as well. But I think it's just something worth us looking at, I think, right now. So if you look at this, you know, let me kind of do some stuff here that I think you're gonna believe. Well, let me, okay, you guys, I always forget, people have, just want to have enough room here, guys. So we have this. Tell you what, A is a constant, sigma is a constant, pi is a constant. Four, pi, and epsilon naught are all constants. Here's A, here's sigma, here's pi. They're all constants. A, sigma, and pi, all constants. 4, pi, and epsilon naught, all constants. Let's pull them out of there. Watch what I've done here. It's a little, you know, maybe it's a little bit on the slick side, but okay, A is a constant. It's not going to enter, I mean, it does have significance. There's no two ways about it. It definitely has significance. But it's not, for the integration that we're going to be doing, it's not going to have significance. Let's put it like that, if you allow me to say that. Okay, now why on earth did we do that? We got to there. I mean, I arbitrarily I could have pulled a lot of stuff out of there, guys. I could have pulled I pulled a lot out already. I could have pulled one more thing out of there, the 2, but it wasn't really useful to do so. Reason being, if you were going to integrate by substitution, take the quantity a squared. A squared's a constant now. Take the quantity a squared plus r squared. R squared varies. R varies. Take the quantity a squared plus r squared, that whole quantity taken to the 3 halves. Why don't you call a squared, why don't you just call the quantity a squared plus r squared, call it u. Well, du then would be, if you said u was equal to a squared plus r squared, du dr would be 2r. du would be 2r times r. Wait a minute. 2r times r is your du. This thing's u right here. You're basically, guys, and I'll tinker with this in different ways. Let me erase this. You all have access to it via the film. Like I said, we can look at scenarios if there's conduction going on and how that's going to play out. And how that gets looked at. I mean, how you look at particular E fields, what might happen. What happens within a conductor and what happens outside of a conductor. We'll talk about those things as we need to do so. Right now, the big thing is the math that we've done here. Are you telling me that if I'm talking about an integral of 2r dr, you know, this kind of an integral looking like this, you got this. We already said the quantity a squared plus r squared is u. We already said that, you know, I mean, if u is a squared plus r squared, du dr is 2r. du is 2r dr. du is 2r dr, huh? Yeah, that's what we said. That's this. Let's not worry about the limits of integration right now, guys. Let's look at this and say, let's not get hung up on that right now. Yeah, that's true. Okay, we're not worried about the limits. Yeah, we're going to take care of this. At the end, we'll put it back to where it was, and we'll figure out what it is. We know how to do this by the power rule. You add 1 to it, and you multiply by, you add 1 to this, and you multiply by 1 over that item plus 1. Let's make a long story short. You add 1 to this thing, and you multiply by the reciprocal of this, which is 2. Ladies and gentlemen, here's your integral. Here's the result of the integral. Great, so what? Well, I mean, not so what. I mean, it's pretty big stuff. I mean, once we get to here, let's do this. I mean, basically, I mean, there's a number of things you can do, guys, and like I said, there's a little more than I actually would want to say. Maybe, I don't know. Like I said, many people aren't going to have the background of this, but many are. So I figure here it is. Go over this if you want. Don't go over it. I'm not going to test you on this if it's a non-calc based class, and this, pertains to what we're doing. So, and this isn't. So, but it's still good to know, you guys. Still really good to know. But if you're not comfortable with it, don't use it. Just use the stuff I'm going to do here. I mean, here I'm going to. We'll talk about that in a second as well. What's going on here? We got this as an answer. What is that? That integral? Yeah, okay, let me still look at it, man, and I still, there's a lot to do here. Now remember, I didn't even consider, ladies and gentlemen, I mean, at least when I walked over there to your left, when I walked over there, I didn't even consider this yet. I'll throw that on when it's time to throw that on, I guess you could say. They're saying this. Yeah, what did we say the U was? They're saying that's -2 over the square root of u. Yeah, I know. To the 1/2. Negative 2 is -2. Negative 2 is -2. U to the -1/2 is, well, u is the square root of the, no, forgive me, it's not the square root. U is just this. U is that. U is a squared plus r squared. End of the story. A squared plus r squared. So, yeah, u is a squared plus r squared to the -1/2. That is a squared plus r squared on the bottom to the 1/2 power, or the square root of it. It's this. Yeah, it sure makes a lot of sense. Sure makes a lot of sense. If you were going to get the derivative, and here's proof that it actually makes sense. If you took the derivative of this guy, which is the same as a lot of ways to go here, guys. Which is the same as a squared plus r squared to the -1/2. If I got the derivative of this guy, I would take the negative, by the power rule, I'm going to do the chain rule also. if I took the derivative of this, which is I'm claiming that's this is the answer I claim. So let's take the derivative of the answer and let's see if we can get to this before you did the integral. The derivative of this by the power rule is negative 1/2 out in front. Bring negative 1/2 out in front. Negative 1/2 times negative 2 is 1. Great. Subtract 1 up here. Subtract 1 up here, subtract 2 over 2, you get negative 3/2. Negative 3 over 2. Negative 1/2 minus 1 is negative 3/2. The quantity a squared plus r squared to the negative 3/2 times negative 1/2 times negative 2, which is nothing. It's just negative. It's, negative 1/2 times negative 2 is 1. Negative 1/2 times negative 2 is 1. The derivative of the power rule here and using the chain rule. So take this out here as the power rule. Negative 1/2 times negative 2 is 1. 1 subtracted from negative 1/2 means negative 1/2 minus 1 is negative 3/2. By the chain rule, take the derivative of what's in here, and that's 2r. Really? So I guess it's 1 times the quantity. It's 1 times the quantity. It's 1 times the quantity a squared plus r squared to the negative 3/2, or put underneath, have it to the positive 3/2, times 2r. Yeah, it's the same answer, so the integral works. So it looks pretty good. Looks pretty good that way. Now let's multiply. Let's get those answers, and let's multiply by a sigma pi over 4 pi epsilon naught. We got all this stuff. A sigma over 4 pi epsilon naught. We had done an integral from 0 to infinity of 2r, and I purposely constructed it that way. It's looking like this. To the 3/2, which is the same as a sigma pi over 4 pi epsilon naught. The integral from 0 to infinity of, forgive me, there's a dr right there as well. There's a dr over here, you guys. Dr, you're doing the integral with respect to r, so sorry about that. That r should have obviously been there. Here it is. And that's the same as saying a squared plus r squared. Underneath here, it's to the, it's 1 over the quantity a squared plus r squared to the 3/2 power. 1 over the quantity a squared plus r squared to the 3/2 power. That's the same as the quantity a squared plus r squared to the 3/2 power. The quantity a squared plus r squared to the 3/2 power, 2r dr. Wait a minute. There is an antiderivative here such that when you take the derivative of the antiderivative through some kind of chain rule, the derivative with respect to r, some kind of chain rule, doing the derivative with respect to some kind of chain rule with respect to r, the derivative of r squared is 2r. That came from somewhere. That 2r kind of solves the problem. Here's your du. This whole thing is u. You got u to the negative 3/2 du, some kind of integral going on. That's simply, that's simply the power rule that we've always known about. What's going on here? You bring the negative, let's add 1 onto this guy. Let's add 1 onto negative 3/2. You get add 1 onto negative 3/2. You get negative 1/2. And take the negative 1/2. and go 1 over negative 1/2 to go over here, and you're getting this. Okay, we've done this a number of times already, guys, but I just want to emphasize there's things jumping out at us even if we don't explicitly use the substitution rules and the substitution methods. We can kind of see there's a way out. Hey, that 2r came from somewhere. Where'd he come from? He came from the derivative of r squared with respect to r. The derivative of r squared with respect to r is 2r. Hey, this is all right. Just do a chain rule here and you're set. You got it right here. And how the whole thing's going to play out, you guys. So that's, there's, you know, and when you actually do it, you get up to here. Now what are we saying here? So without further ado on this thing, A sigma pi 4 pi epsilon naught. And again, we do the derivative here. Where did this come from? Well, here's the du. Here's the du. Here's the u. It's pretty easy to do at that point. It's u to the negative 1/2 times negative 2. What does that mean? Well, it's negative 2 times u to the negative u. I'm sorry, it's negative 2 times u to the negative 1/2. Times u to the negative 1/2, and what is the u? It's going to be this. It's going to be this. You know, and how that's going to, and how we're going to play that out. How does that all get played out? And that's the integral from 0 to infinity. So you're looking at this. Usually the easier way to look at this stuff when there's involving radicals and there's a way out of it, probably deal with positive radicals. If there's a negative radical present, just do some kind of, you know, then get the reciprocal of the quantity that has the negative radical in it. If it's just one negative radical. If there's negative exponentiation going on, work with the reciprocal of that, you know, don't work with the reciprocal. I'm saying if there's some negative exponentiation going on, then 1 over the positive counterpart of that exponentiation. X to the negative 2 is the same as 1 over x to the positive 2 is what I mean. So you're dealing with you're exploiting the fact of what reciprocals are all about. So you're looking at something like this, and this is where it's going to play, and it should come out pretty neat. It answers, obviously the way they discussed it with Gauss's law, it's a little easier, but this to me is more of a gut feeling as to what's actually going on here. So we've got all this. And what's going on? Well, a lot's going on. I mean, there's pi and pi cancel. Negative 2 and positive 4 cancel. And you got a negative right here. Put the negative right there. What's going on? Well, I've got negative a sigma over epsilon naught. And then everybody's kind of like falling out of this thing. And we could throw this guy on here later on. Doesn't matter where you want to go with this. You're starting 0. Just as long as there's consistent mathematics throughout, guys. It's a square root. It's a square root. What's going on? Well, let's see what's going on. Let's put a 0. Let's go from 0 to infinity. Let's put a 0 in for r right here. A 0 in for r right here. R squared is 0 squared, that's just 0. A squared plus 0 is A squared. The square root of A squared is A. You've got, okay, you're going from here to here, so this is going to be the minus on that. So what we have here, let me put a minus right here, get rid of this. Here's your minus. Let's try something else. Let's go another way here. There's this right here, and we said it was a positive, right? There's a positive amount of charge. We wouldn't have a tremendously difficult time dealing with conductors either on this stuff, guys. I think the argument's pretty sound no matter how you want to go about it. Different logic at the end of the day, but the mathematics, there's tremendous similarities in all the mathematics. Go for infinity or something really big going toward infinity. Something really big going toward infinity. If R is something really big, when you square it, it's massive. Something massive plus A is something, yeah, I guess you could say it's more massive than really massive, I guess you could say. The square root of something really massive is still massive. 1 over something massive, 1 over a positive number that is massive, 1 over a positive number that is massive is very close to 0. Tell you what, I can get it as close to 0 as you want. As you go toward infinity, if this is really, really, really big, A squared plus R squared is really huge. The square root of really huge is still really big. You know, like let's put it this way. If the number under consideration close to infinity is not infinity, but it's a big number, and I were to say to you, okay, well, it's really, really big, huge. Okay, it's huge. If it's huge and you square it, it's really huge. And if you square root that, or something a little more than that, it's still going to be really huge. 1 over something really huge is close to 0. As you go to infinity, you guys, this infinity thing goes to 0. On the other side of that, put a 0 right here. 0 right here. 0 squared is 0. 0 plus A squared is A squared. The square root of A squared is A. Zero minus a negative is going to be a positive. A sigma over epsilon naught times 1 over A. What's going on here? You know what's going on. The A's cancel. The E field is straight up from that point. The E field is straight up from that point. This is for a non-conducting surface. For some reason, guys, I think I put, there was a 4, the 4 and the 2 didn't cancel. There should have been a 2 right there. I'm sorry about that, guys. This is the 2 right here, 2 right here, and that's a 2. I don't know how I canceled it. I think when I canceled, and there it is. There's your answer. When I canceled, guys, there was the A sigma pi over 4 pi epsilon naught, and then I had a negative 2 over here when I did that, associated, you know, just trying to figure out what exactly I'd said. Yeah, I brought it down there. There was a negative 2 right here, guys, and there was a 4 here. So, right, so when you're doing that, negative 2 here, and you got the A squared plus R squared. Yeah, I'd had that somewhere, and of course that's the stuff I exactly erased. When you actually did this guy right here, when you actually did the integral right here, that's where you got the negative 2. That's where you got the negative 2 times, u to the negative 1/2, which is equal to this. And right, and then that's how we were doing it, guys. So you had this right here. The -2 and the +4 cancel, and that's a see, I neglected to put the -2 at the bottom. They cancel, and you got a -2 on the bottom. -2 on the bottom or a +2 on the bottom, but it's got to be somewhere. The pi's cancel, and you got a sigma over -2, right, epsilon naught. A sigma over -2 epsilon naught. The pi's cancel, the -2 and the +4 cancel, and there's a magnitude of 2 here, a -2, so to speak. A sigma over -2 epsilon naught. A sigma over -2 epsilon naught. Well, the negative you can bring up here, and you got that. And that's how it should have played out, you guys. The 2 stayed. No harm done. We caught it. I don't like disrupting the flow like that, guys, but it's going to happen sometimes. You go to here, like I said, the 2 and the 4 cancel. The negative and the positive cancel. There's a negative right here. Fine, leave the negative right here. Put a 2 right here. The pi's cancel. You got negative a sigma over 2 epsilon naught times 1 over the square root of the quantity a squared plus r squared, evaluated between the limits of integration 0 and infinity. When you finally do that, pretty important conclusion. Hugely important conclusion. When we're dealing with capacitors, we're going to use this mathematics to talk about, the E field between a capacitor plates. There's something crazy going on here. Look at this E field. The E field is perpendicular to the plate. If there is another plate, not with positive charge associated with it, but with negative charge associated with it, it'll add to the E field. If you're just considering that plate with the negative charges on it, like I said, there could be a positively charged plate here, negatively charged plate there. It's a capacitor. We use that to do the capacitors. You're doing conductors there, but the argument is the same. The mathematics is essentially we already have the mathematics that we need. We just saw it. We just saw a lot of it. Some of the argument that we need, we've seen it. What's going on here? This E field is perpendicular to that infinitely long plate, and the E field does not change regardless of where you are in relation to the plate. You could be the positive test charge, say it's all positive, we're dealing with positive, the plate was positively charged, right? It was a non-conducting plain sheet of charge, and we wanted to see how it acted and everything else. This could have been discussed in other ways as well, I guess you could say, but that's neither here nor there. For our purposes, it's a non-conducting sheet of charge, and I do not care if it's a positive sheet, non-conducting sheet of charge. No, the charges aren't moving, they're right there. They've done that. If the positive test charge is just above the surface, you think, it's got to be a great E field that it's experiencing. It must be an incredibly big E field that is being experienced by the positive test charge if it's just above the surface. You know, treat the ground that I'm standing on right now as that sheet of charge. And I want to say, wow, there's a small charge just above the surface. It must be experiencing a tremendous E field. Of course, going upward, that was our conclusion. It is going upward. Everything else canceled out. It doesn't matter, though. If that's an infinitely large sheet of charge, the positive test charge wouldn't have to be right next to it to experience the E field that it experiences, whatever it may be. Maybe it is a great E field. Let's say it's something. It's a great E field, a massive E field. Yeah, sure it is. It is the exact same size E field if you take that positive test charge and move it 100 miles away. The positive test charge was 1 centimeter above the surface, and it experienced a massive E field. Okay, maybe it did, maybe it didn't, depending upon how much charge is on that surface, on that sheet of charge, depending on how much is there. Yeah, if there's a lot, okay, sure. If it's really dense, you know, and it's very densely packed and everything else, sure, fine. The exact same massive E field will be experienced by the positive test charge if the positive test charge is 1,000 miles above that infinitely large sheet. The sheet has to be infinitely large. Otherwise, you got to work with approximations. I can't use that. It literally would have to be an infinitely large sheet of charge with charge density, surface charge density, sigma. If the positive test charge is 1 centimeter above that infinitely charged surface, or if it's 1,000 miles above that infinitely charged surface, it is the same E field it's experiencing straight up. It's got to be infinitely big. If it's finite, there's other there's much. Then it doesn't work that way. If it's finite, you're allowed if the distances involved are not tremendous, you can make this assumption even when it's not an infinitely big sheet of charge. Exactly when and how, we'd have to look at that. We'd have to see what's allowed. We'd have to look at some mathematics to do something like that. But for our purposes, that doesn't depend. The E field goes straight up. The resultant E field, after all that pushing around, goes straight up. No matter where you want to locate the positive test charge. You know, 1 centimeter above the surface, if the blackboard were that surface and went out infinitely in all directions, 1 centimeter above it, or 1,000 miles away, or 1,000,000 miles away. Technically, it works. The mathematics tells us it works. Now, where are you going to find an infinitely large sheet of test charge? Literally infinitely large. Well, that's another thing. So you'd have to approximate. I can pretend it is for certain if I'm close. If I'm pretty close, relatively close to the surface or something like that. We'd have to look at some math on that. Anyway, it's a fascinating discussion, you guys. The Serway and Vuille book, guys, like I said, these 18 problems, they'll scroll at the back. Let me do what I can here. The initial plan right now, as I'm talking to you right now, is to try to do these 10. 4, 14, 15, 20, 31. Yeah, right. 4, 14, 15, 20, 31, 55, 56, 58, 60, and 66. Those 10. Let me see what I can do. All right. Sorry I kind of approached this thing somewhat in reverse, but I thought it was an important enough topic when you see something like this. How would you do it if if you're talking about a conductor and stuff like that? There's stuff we'd have to sit down and look at it, but man, the mathematics is very similar. This is a lot of the mathematics, and again, Serway and Vuille go into it just using Gauss's law, which works great. To me, if we can somehow get a feeling for this, for those of you that have the background, this isn't a bad feeling to try to get and to try to look at this intuitively. If you don't have this right now, you'll have background in it in the future, and if you don't, so what? Who cares? I mean, just don't worry about it. There's other things that can be done, but I would advise. I mean, be able to look at something like this. I think it helps you out very much. All right. See what we can say here, guys. Let me get these out of here. All right, guys. So let's look at, from what I've been telling you guys, let's look at again, when we get just based on what I said, when we get to capacitors, you're going to be pretending, wow, those are relatively speaking, the capacitors, they're not that far apart, and the plates are really big, so you can pretend they're infinitely large. And if one of the plates is negative, one of the plates is positive, they're actually helping each other to create double the size of the electric field. What's double the size of an electric field that is sigma over 2 epsilon? Sigma over 2 epsilon, when it's doubled, is just sigma over epsilon. And that's how it's going to happen later on, you guys. I just want to kind of say that. There's not a whole lot of difference in that regard when they talk about it. And then the E field outside of the plates, they cancel each other out. And Serway and Vuille go into that in really neat detail. Number 4, and again, you guys have the book, and you got the solution scrolling at the end, you guys. So let me try to go relatively at a good pace on this. For number 4, a small sphere of mass m equals 7.50 grams and charge Q1 equals 32.0 nanocoulombs is attached to the end of a string and hangs vertically as in the figure they're going to show here. I'll show it as well. A second charge of equal mass and charge Q2 is negative 58. Negative 58.0 nanocoulombs. So one's 32.0 nanocoulombs, the other one's negative 58.0 nanocoulombs. So let me think here. Is located below the first charge at a distance of 2 centimeters. Find the tension in the string. If the string can withstand a maximum tension of 0.108 newtons, what is the smallest value D that you can have before it breaks? So they're trying to say some stuff here, guys. Let me leave it and let me say it in some ways, I guess. One's positively charged. One's is this. They're saying that they both got the same mass now, right? I mean, they're both. This is Q2. And they're saying that, the mass, and they're trying to say here, find that, there's 2 parts here, I guess you could say. You got mass. Q1 saying a couple things here. Distance D is 2 centimeters. Usually you're converting all this stuff, guys, to the MKS system of units. Find the tension in the string. I guess some of this stuff, it's held there. it's held very strongly and can it make it push? I mean, there's a lot that can go on here, guys, that we see. So how you want to look at it. I think this thing's kind of held in stone, so to speak, and then I can pull on the other one, and there's going to be a tension experienced and everything else. Find the tension in the string. Find the tension in the string, and if the string can withstand a maximum tension of 0.10 newtons, what is the smallest value D can have for this thing to happen? We're going to ignore the negative. You know, there's a lot of ways these problems can be done, guys. I guess you got to play the rules according to the way they're making the assumption. Sometimes assumptions are not always. Sometimes the assumptions that are to be made are not always very obvious, I think. So let's see what we can say. Ignoring the negligible gravitational I'm having a hard time reading my own writing here, guys. Hold on here. Ignoring the negligible gravitational force between the two small objects. You know, they kind of looked at it. They kind of, you're not worried about their gravitational pull with one another. It's pretty negligible. But they do say this: what kind of tension is going to be experienced? Well, if you're going to be holding that guy there, somehow there's somebody holding the charge there, not letting it move up or down or anywhere. There's going to be a pull here, and let's figure this out. Well, the pull is the tension's going to go straight up. It's going to fight the pull that's going on between these guys. And let's find out what kind of a pull it's going to be. Well, the tension, first of all, has got to hold on to mass 1. Mass 1 equals mass 2 equals mass. The mass of these. You got this. Plus Q1, Q2 over D squared. Yeah, it'll work. Plug in the numbers. Plug in the numbers. I mean, they're crazy, but be careful. You know what nanometers are? You know what this thing is? And I got, like I said, I got this scroll down at the end as well. But you go in here. True. All right, there's your tension. 0.180 is the maximum tension this guy can handle. Are you over it? No, you're fine. 0.1152 is about 0.11. 0.1152 is about 0.115. 0.12. It's about 0.12. 0.12 is smaller than 0.180. So not too bad. Not too bad. You could make the tension about 1.5 times more than what you got right now, and then maybe there's an issue. Tell you what I'm going to do. Let me find. They told you that's for A now. See what we got. Well, look, let's go down the line here. They talked about positive, negative. We're not gonna worry about that. It's really it's got to be absolute value K Q1 Q2 over D squared. I get that. Let me just I don't want to confuse it. I can put a negative in front of the negative Q, and then I'm okay. Technically, it is what it is. It's gonna be a negative quantity, is what it is, guys. Right here, this is a negative product. Tell you what, I'd rather kind of write it like that, and then Q2 is a positive. This is what it's kind of what it means. I don't know. I got a feeling I'd be confusing you more than I'm going to help you. So you're going to see it in the stuff that scrolls down, you guys. Just talk about absolute values as they are. Kind of have that in the back of your mind. Do not let this be a negative. I don't want it to be a negative. I know it's a negative. A negative goes down. The weight also goes down. And then the tension is going to pull upward. So they are, in terms of magnitude, write it like this. Let's talk. This is very important. Be careful here. I mean, don't put negative numbers in here. I want a positive answer. Why do I want a positive answer? Because they're both pulling. Mg is pulling down, and Kq1, Q2 over R squared is pulling down. And tension's going to equal it and go opposite to it. Okay? Let's see what we got. Look, they're going to tell me there is a maximum T. I'm going to put the maximum T right in here. I'm going to put the mass of M1 hanging down. G is the acceleration due to gravity. K is what it is. Q1, Q2. Make them both positive. Make sure the answer is positive. That's why I kind of did the monkey business I did over there earlier. Okay, be careful. I want to find the D that'll take it to the breaking point. Solve for D then, please. Why don't you divide by that quantity on each side and multiply by D squared on each side? True. Square root each side. And that's it. You plug in, I mean, that's the big thing. That's really, really the big thing, guys. Absolutely true. Put the point, point whatever, that's the point. This is the 0.18. This is the, the 7.5 grams times, times the 9.8, et cetera, et cetera. Plug everything in there. It's got to be plugged in there, guys. When you do so, that's it. That's the big one. Sorry, guys, I'm not using the right color chalk sometimes. Grind this out, guys. I mean, this is the big thing right here. (1.25 centimeters). Which is the same as 0.0. Let's have a look. 0.0125 meters. I mean, typically, the language they're speaking is the MKS system of units. And that's number 4. 14. For number 14, they're saying, guys, two identical metal blocks resting on a frictionless horizontal surface are connected by a light metal spring having spring constant K equals 100 newtons per meter. An unstretched length, L sub I, is 0.40 meters. A charge Q is slowly placed on each block, causing the spring to stretch to an equilibrium length of capital L is 0.50 meters. It went from 0.4 to 0.5. Determine the value Q, modeling the blocks as charged particles. To make that happen. That's a pretty neat question. Okay, guys, they're saying all right, guys, the way you want to look at it, now they put the same amount of charge on each one and the same sign. So we're not going to get caught like we did last time, positive and negative, and think, oh, wow, I was kept using absolute values, right? You're not going to have to do that here. So they got two, there's a length, there's two, you see it in the book as well, guys. There is... And this is when there's no compression and no extension. And when you put the charges on them, I mean, this is all exaggerated. The scale's not great, but and that's after you put the charges on them. You put the, and there's, like I say, a spring constant K, a spring constant K, and this is Q on it, and this is Q on it. Masses are the same, the whole thing, but this is what happened here. Charge Q is slowly placed on each block, causing it to stretch to the equilibrium. So determine, modeling the charges. So find out, find the value of Q. There's Q placed on each one, guys. A charge Q is slowly placed on each block. There's Q on one block and Q on the other. I mean, you got to really watch the language, guys, how we say this stuff. Basically, whatever the spring does for force and whatever electricity does for force is equal, because they're not moving outward and they're not moving inward once you've done what you had to do. Okay, sounds good to me. Yeah, it got this long, it was this long. The difference between the two is the x. Kx tells you the strength. Force electric, K sub E, that's 1 over 4 pi epsilon naught. So it's a K sub E, not the same K as this. Q squared, Q times Q, over L squared. Guys, we just said those two are equal. If they're equal, make them equal. Write them down like they're equal, because they are. What do we got? Force electric. That's how far apart they are. It's point particles. That's it. I mean, that's the crux of it. That's the thing, guys. If you get to here, the mathematics is fully under, you get to here, you ought to have the mathematics fully under control. It's as simple as that. The rest is math. Solve for Q squared at least. Multiply by L squared over KE on each side. Square root each side. Yeah, like I said, there's a lot of ways to go here, guys, and you know a lot of the stuff anyway. Take the square root of each side. I think I showed it a little differently in my notes. A little bit differently in my notes, but not a big deal. That's L. Let me kind of put the square root of L squared. There's an L squared there. I don't know, whatever. It's a horse apiece. I wrote it I was a little different in how I wrote it, but I said there's a little bit of a difference there, but not much. The square root of L squared. Square root of L squared is L. The square root of all that. Okay. You plug in all the numbers, guys. Take what they gave you. Now remember, everything is in terms of. They prefer like final answers, unless they ask us otherwise. They're preferring final answers in the MKS system of units. You're talking about coulombs, you're talking about newtons, you're talking about watts, you're talking about joules, you're talking about meters, you're talking about seconds, okay, et cetera, et cetera. Unless they tell us otherwise. So, watch what's going on. They've given you. They already gave you this. They already gave you that. You got this, you got that. This is the same as that. Deal with it. At the end of it, guys, $1.67. Yeah, they all mean the same thing, guys. Okay, neat stuff. Let's go to 15. 15. Two small metallic spheres, each of mass m equals 0.20 grams, are suspended as pendulums by light strings from a common point, as shown, and we'll write it down. The spheres are given the same electric charge, and it is found that they come to equilibrium when each string is at an angle of 5 degrees, the regular degrees we're used to. Radians are very popular. They are the language, they are the degree measure of science. They're very, especially physics. But like I said, they tell us play 5 degrees, we can play 5 degrees. We know how to do it. They come to equilibrium when each string is at an angle of theta equals 5 degrees with the vertical. If each string has a length of 30 centimeters, what is the magnitude of the charge on each sphere? Okay, the spheres are identical. There's a lot going on here. Let's determine a couple things, guys. Let's see what we can say about that. All right, guys. I approach this in various ways. I for some reason, trying to believe some of what I'm doing here. Okay, it should be okay. They're telling us the masses are the same, the length here is the same. With the vertical, they're telling us that's theta. That's also theta. Pretend I know how to draw, guys, which is quite a stretch. This is x, this is x. Not really the same size, but pretend they are. The distance between them is 2 times x. We got to talk. There is a tension T right here. There's a component of tension Tx and a component of tension Ty. Okay, I'm not thrilled with the drawing, but hopefully you can see it, guys. You're looking at a situation. Let me maybe kind of put it over to the side as well. There is mg going straight down. There is Ty going up. There is Tx going this way. And there's the force electric going the other way. You get where I'm going. Let me try to, maybe I should take a snapshot. Let's take a snapshot of that, guys, what just happened. This is T. This is Tx. This is mg. This is Fe. Let's get it straight. The Ty is as big as the mg. The Tx is as big as the Fe. And that's going to solve it. That's the hardest part of the problem, you guys. Ty is as big as mg. Tx is as big as Fe, and that's as big as kq squared. The same amount of q on each one. D squared. Now d squared is x and x put together, so you better be careful there. You know, it's not just this. It's not just this. It's not just this. It's x and x. So we've got to be careful. I know there's an x right here. I mean, nobody's denying that there's an x right here, and maybe this can answer something for us, but that's not the x associated with r. R is 2x, or the distance d, it's 2x. So be careful here. Be careful. Number of ways to look at it, I guess. Let's go back to the handy triangle, I guess, right? This is theta. This is as big as mg, and you know, up here the pull up is mg, so the pull down is mg. That's doing that. This is 90 minus theta, and this is that, and this is as big as t is. There's a lot of ways you could go here. I don't know if I'm, whatever. It's neither here nor there. Let's say this. The tangent of 90 minus theta, is the rise over the run. That's the tension too. Tension components. Ty over Tx. So what do you want to say? We said it was the length of L, right? Is it true that isn't x right here, isn't x the same as, that's the length of this, and the size of the forces are analogous too. The forces, how they interact in many regards, and distances under consideration are directly proportional to one another, which makes sense. Because if something's being accelerated, Twice the acceleration for the same something means twice the force. Twice the acceleration means twice the distance traveled. So there's a correlation between distances and forces. I'm not sure. I'm not sure I want to say this all the time. There's probably there's going to be some other circumstances that may come into play if you're with maybe some other. Well, Gary, never say never, never say always. So often, however, for our purposes, there's going to be that correlation for sure. So often there is that correlation. And again, it makes sense. If the acceleration is twice as big on a given object than it used to be, twice as much force is on it. True. And twice the acceleration means twice the distance traveled. Yeah. Or 10 times the acceleration associated with the object than it had earlier, 10 times the force. 10 times the acceleration means it's going to cover 10 times the distance too in a given period of time. If it's a constant acceleration, again, there's a lot of things that can happen, guys. But that's for our purposes. There's correlations here that are of interest. This right here, if this is x, and if this length is L, and this length is x, then x over L is the sine of theta. X is equal to L sine theta. True. Multiply it by 2, you get what D is. You get what D is. All right, so let's see what I want to say here, guys. How we're going to say this. We said what D was. D is equal to 2L sine theta. So what we're going to do is we're going to say, I didn't even want to go this way, to be honest. Well, we can. It doesn't really matter. Can I ask you a question? Is that the same as, is this ratio right here the same as the tangent of theta, the inverse of the tangent of theta? Look, let's get this straight. mg over this is the tangent of this. Yeah, true. The tangent of theta is this over mg, so the inverse of the tangent of theta will be the same thing as that. Let's keep theta rather than 90 minus theta. 1 over the tangent of theta is going to be mg q squared over d squared. D squared is the quantity 2x squared, is the same as the quantity 2L sine theta. Yeah, it is. It's a mess, but let's see where it goes. 1 over the tangent of theta is equal to this as is. This flips over and gets up here. Square this, you got 4L squared sine squared. Yeah, that's true. That's true. So you get it to here. Okay, we're trying to find the charges, guys. I mean, what we're trying to do. How do we find the charge? It's that guy right there. We can get the reciprocal. If two things are equal, their reciprocals are equal. And then you got q squared on top, and then you just eliminate q squared. I got a better idea. Why don't you multiply by q squared on each side, and multiply by tan theta on each side, and I think you're good. do it again. Over there in the green, multiply by q squared on each side. Multiply by q squared on each side and multiply by tan theta on each side, and you're pretty much in business. Over K. Yeah, it works. I mean, it's a little bit of a mess. I'm not, I don't know. You can argue this process right here. You could have almost come right over here and say, hey, look, man, let's just find tan theta. Let's find tan theta. Tan theta is going to be this over that. Yeah, it's probably the easiest way to have done it. The way I had done it in my notes is a little more awkward than I would like to have done in retrospect. I mean, you could have gone and looked at it and say, well, let's see if I can solve this. They gave me, it doesn't matter. You can deal with this. You can put stuff in there. You can get answers. It works. It all works. It works. This works just fine. If you know it's 5 degrees, if theta is 5 degrees, 90 minus theta is 85 degrees. If theta is 5 degrees, 90 minus theta is 85 degrees, no big deal. The math's going to be consistent, it's going to work. I think in retrospect, tan theta is kq squared over d squared divided by mg. That's tan theta. Go that way. Watch your step, because you got to find what d is in terms of the data that they gave you. There it is. And it'll work. It'll work. In retrospect, that's a better way to go. If you'd have gone tan theta equals this divided by that, bam, the whole thing will happen. The whole thing will happen. You're going to get the exact same answer. That's not going to be an issue. Let's not, as such, I don't want to make it too big of a deal. Why don't you square root both sides? If you square root all this, you've got 2 2L sine theta mg give a little more space here, guys. It's probably a trivial circumstance what I'm trying to say here, but I mean, at least my meticulousness with this. There it is. When you do all that and you plug in the appropriate values, you got to watch the units. You want to make sure the units are on. I mean, they're going to give you all kinds of units, guys. They're going to give you all kinds of units, which are fine. It's good that they're doing that, because that's the reality of it. Some of this stuff doesn't lend itself to, hey, please just plug in everything and you'll be fine here. Well, it doesn't always work that way. You gotta work with what you have. So it comes out to 7.22 times 10 to the negative 9 coulombs. 10 to the negative 9, those are nanocoulombs. So on and so forth. That's 15. Number 20, relatively easy one. Problem number 20. They're saying an electron is accelerated by a constant electric field of magnitude 300 newtons per coulomb. A, find the acceleration of the electron. B, use the equations of motion with constant acceleration to find the electron speed after 1.0 times 10 to the negative 8 seconds. Man, after only 10 to the negative 8 seconds, assuming it starts from rest. What's going on with that? So that's problem number 20. And again, all of these guys that I initially had written on the board, all 18 of these, are going to be scrolling at the bottom of the video, or at the end of the video. They'll be scrolling at the end of the video for us. Okay. Okay, so you're talking about acceleration. Number 20 again, guys. Number 20, an electron is accelerated by a constant electric field of magnitude 300 newtons per second. Find the acceleration of the electron. B, find the equations of using the equations of motion with constant acceleration. Using them with constant acceleration to find the electron speed after 1.00 times 10 to the negative 8 seconds, assuming it starts from rest. All right. Well, you want to look at it. Force equals QE. What's Q? Well, Q is E, small e. The charge on an electron. Don't worry about positive or negative. It's going to go one direction or another, but the charge on the electron times the magnitude of the E field will tell you the force that's on the electron. That same force is manifested, or at least seen, I guess you could say, manifested by mass of the electron times the acceleration of the electron. To make a long story short, yeah, they're equal. Well, I mean, we just said it. I mean, F equals F. MEA equals EE. That's all it is, guys. It's coming out to this. All that we need to do at this point is talk about the specifics. If you plug in, that's it. I mean, that's it. That's going to get you there. This is what it's all about. This is the mathematics behind it to get that acceleration. What does that mean? Charge on an electron is that 300 newtons per coulomb. There's this many coulombs on the electron divided by the mass of the electron. chalk, guys. Sorry about that. This is the mass of the electron, though, guys. Mass of the electron in kilograms. This is 300 newtons per coulomb, and this is coulombs. Everything's MKS. The acceleration is going to be meters per second when we get it. It's remarkable. Regarding what they're saying here, let's see what kind of numbers they're getting. To say that this is a great acceleration is an understatement. Watch this. I mean, it's going to be times 10 to the 13th. That's tremendous. That is some kind of acceleration. With that kind of acceleration, it's probably not going to take long to be going very fast for our purposes. Yeah, we know that. We said this thing started from rest. That means zero. That means magnitude of velocity equals 0. That's moving after, in no time almost kind of thing. I mean, it's just, after a very short period of time, I'm looking at this thing. You'll see it too right now, if you've not already seen it on canvas. This is something else. And there it is. .27 times 10 to the 5th meters per second. That was 20. Let's go to 31. 31, there is a figure that they show for us. There's a negative charge and a positive charge. In this figure, they want you to determine the point other than infinity at which the total electric field is 0. Let's take a look at that. That's number 31. Number of ways to go here. Let's talk. Let me draw it, and we'll talk a little bit. Let's draw it. Let's use our common sense. Let's argue with ourselves a little bit about how to proceed with number 31. After I draw it, let's take a look at it a little bit. Well, where? Other than infinity, guys, where's this going to be? You know, where's the net electric field in this thing? You know, when's the total electric field going to be 0 other than at infinity? They put about a meter between them. And let's see what kind of argument we can make here. There's a negative here. There's a positive here. What's going on here? Well, look, I mean, a couple things just jump out at us, guys. There's really not a third charge anywhere. If you had a test charge, yeah, there's your third charge. But I mean, in addition to the test charge, there's not a third charge anywhere where you can kind of like orient these guys possibly in some way, or maybe with 4 charges in addition to the test charge, or you know, the test charge and 3 other charges, or the test charge and 4 other charges. There's only 2 charges here. Look, I mean, if there was a single charge here, and I don't know, I guess perhaps there is a location where this could actually be made to happen. I think we could do it. If we had a third charge and we positioned, if there were 3 charges here and there was a 4th charge called the positive test charge, that's the way I should have said it a while ago. A little bit from now. If there was like 3 charges and somehow oriented in some way in 3-dimensional space, could I do something? Could I locate a positive test charge somewhere between them and it could work? It sure, let me try to think about it actually. Yeah, I sure could. I sure could. I could do it. I'd have to look at, you know, you'd have to look at the E fields and the E fields that are generated at a particular point, and then you'd say where it goes, and there's no, yeah, you could do it. I could go in 3-dimensional space, and in a 2-dimensional plane where all 3 charges are, I could put a positive test charge in the right place, so to speak, and the positive test charge would be somewhere between those 3 charges, or perhaps not even between them, you know, but somewhere in the plane of those 3 charges. 3 points determine a plane. In the plane of those 3 charges, I could do it, you know, in many, many circumstances, if not in all circumstances. It can be done. Mathematically, we'd sit down, look at it, we could do it. That's not going to be an issue. We can do something like that. You can't go above that plane, though. If you go, you know, even there, it would depend where they are in that plane. If they were all coplanar, none of them collinear, and you went off of it, I think there's no way that could happen. If you could go off the plane itself and still be in 3-dimensional space. I mean, you're in 3-dimensional space with the 3 points on the ground, and I'm talking about 3 points, not counting the positive test charge. So counting the positive test charge with those 4 points, they'd all have to be coplanar. And if they weren't collinear, you could do it. If they were collinear, you could still do it, but you'd have to stay on that line. You couldn't go. So in this, I'll try to make a long story short here, I guess. A lot can be done, and a lot would have to be looked at. Now that's the proverbial riddle we don't want to go into right now. But like I said, if you got a positive test charge and 3 other charges which are coplanar with one another but not collinear, you'd have to have all 4 charges in the same plane somehow, and you could do it. If you had 2 charges and then you have the positive test charge it'd have to be collinear with what's going on over there. It'd have to be collinear with those two charges. You can't have it off of that line because it's the way it's going to get pushed around too much. It's going to the same way that you couldn't go off the plane for the 3 charges plus the other the positive test charge. They all got to be coplanar. Here they all got to be collinear. It's even more restricted in a sense with just these two. With 3 they got to be coplanar. With 2 that you got right here, they've got to be collinear. Can it be done? Yeah, for our purposes, microcoulombs and microcoulombs are the same measuring stick, times 10 to the negative 6. I'm not going to worry about that. I don't have to worry about that. They're the same measuring stick. As long as they're proportional, I can work it. As long as I got the measuring stick set up in such a way that they can be done, they can be looked at, I'm not going to worry about it. I'm not going to worry about it. 6 is stronger than 2.5. The absolute value of 6 is greater than the absolute value of negative 2.5. If you're going to have, and another thing, you can't go over here because this ain't strong enough to fight this guy pushing, which is a very big number, absolute value-wise, compared to negative 2.5. This will just push it right out of there. Can't do it. Within here, this guy will push, this guy will attract, and they'll go right at each other. You can't have that either. I want it so that that there ain't any movement of that positive test charge. The only place that's going to happen is somewhere here. Somewhere there. Where? Your guess is as good as mine right now. Okay, so you got this. What do you want to say? Well, here's what I think we got it. I mean, I think basically we're talking about a situation where the E fields are going to be the same. The E field's got to be equal and opposite. So this guy's gonna have an E field. You put the test charge right here, guys. The E field here is going to go that way. The E field here is going to go that way. They're going to be equal magnitude, opposite direction. Well, let's not worry about negatives then. K, Q. We're not worried about sign. That one's close. Yeah, you got to be close because you don't have a lot of strength in regard to charge. This guy can afford to be further away and still make it. That's it. That's the hardest part of the problem, guys. That's for the 2.5 guy. I don't care about negative. I know this guy's going to pull them. I know this guy's going to pull the positive test charge positive. And I know this guy's going to push the positive test charge in the negative direction. And they're going to balance out. Here's K. Here's 6 times 10 to the negative 6. Divide by 10 to the negative 6 on each side. Divide by K on each side. We've got that. Yeah, we do. You can do a lot. I tell you what. I mean, the 2.5s. The big thing is, guys, get to here. Let's multiply each side of the equation by 2, and maybe I don't want to deal with any kind of. Let's not deal with fractions or let's not deal with decimals any sooner than we have to. True. We could probably argue this a bunch of ways. I mean, if you really want to talk about it, the thing is, you don't want to lose solutions that might work. If you pick up solutions that aren't really valid in terms of the reality of the problem, that's another story. But we're not, I tell you what I'm going to do. If two things are equal, I mean, they're equal, is justification for that. You got 12x squared equals 5, 1 plus x, the quantity squared. 12x squared. This thing right here is 1 plus 2x plus x squared. $12x squared is 5 plus 10x plus 5x squared. Let's get everything over to the left-hand side. Let's add a negative 5x squared on each side. Let's add a negative 10x on each side. Let's add a negative 5 on each side. 7x squared plus a negative 10x plus a negative 5. I'll write it over here, guys. I didn't really want to go that way, but I did. I probably could have done this another way. I'm just worried that I'd lose a solution. I'd rather this thing comes out to be a quadratic equation, two solutions. They both might be valid, probably not. The only way this is going to work is if x is over here. X is a positive number over there. Well, if you're going to do I think we got this. Yeah, I mean, it's like this. You end up doing the quadratic formula. It's a little out of control, man. What you're going to do, I have the quadratic formula for you. It's going to scroll for you at the end, like as we said in the video, guys, so you can go ahead and look at it. We ended up getting, when you do the quadratic equation, you got x is equal to the opposite of b plus or minus the square root of the quantity, b squared minus 4ac over 2a. We know that. Plug in the appropriate value. Notice how I left everything. Positive 7 plus, positive 7x squared plus a negative 10x plus a negative 5. Okay. Deal with it there, guys. X equals 5 plus or minus 2 square root of 15 over 7. Yeah, this square root of 15 is a pretty big number. Square root of 15 is almost equal to 4. Almost equal to 4 times 2 is almost equal to 8. 5 plus almost 8 divided by 7 is about 1.8 something. 5 minus something, almost equal to 8. 5 minus something almost equal to 8 is negative 3 divided by 7. It's going to be a negative number. You can't, there's no, I guess we could explore that too if you wish, but it's nowhere on there. Given the conversation we had before we did this problem, it was nowhere on there. It was nowhere on there. The only place it could be was x, and x is going to be a positive number indicating distance. Negative number was not going to be acceptable. So it's to the left of the negative 2.5 microcoulomb charge. It is about equal to And again, we were confident there was going to be an answer, guys. So if something happened, I mean, we could have maybe taken a shortcut. We could have done some other stuff to make this happen. You know, there's stuff I'm kind of thinking about. You could have done, you know, you could have gone, you know, the quantity 1 plus x squared, multiply that on each side, divide by 2.5 on each side, and you got 1 plus the quantity x squared over x squared. The quantity 1 plus x, the quantity 1 plus x squared over x squared, 6 over 2.5. You know, you could have gone here. You're going to get the same answer. I mean, you could say, okay, what's up? What are you talking about? I didn't do this, but I mean, I'm saying you could have done this. This could have been done. 6 divided by 2.5 goes in twice. So, I mean, 6 divided by 2.5 is 2.4. So what you have is square root both sides. You know, just for the sake of argument. I mean, we did what we did. We're fine. I mean, we're fine, guys. I'm just saying, sometimes you got to go kind of the long way, the way I did it. Don't take too many risks there. X goes into 1, x goes into x. X goes into 1 over x. X goes into x one time. Subtract 1 on each side. Plus a negative 1. You know, unfortunately I don't know if I have a calculator. I might maybe look. I got a feeling it's going to be the exact same answer, guys. I mean, there's no reason it shouldn't be. The thing I'm a little concerned about is when you're doing this, you're only getting one answer. So you got to be careful. The way to get around not getting just one answer is when you square root both sides, you make this thing plus or minus. You make that thing plus or minus. It's probably the way to go. And you're going to get two answers there. I mean, when you actually do it. Don't have it. I don't think I have the calculator on me, guys, to be honest with you, unfortunately. Maybe I do. My knowledge, I don't have it, guys. This should work. This plus or minus thing here is going to guarantee the two answers. Not that you really want two answers. I mean, you don't need the two answers. You don't. In this instance, you want it to just be one answer. You're throwing the other one out the window. So that's the answer. My argument here, the other way to look at it, kind of horsing around with this a little bit, doing all this stuff, and getting it to about here, and then you figure you can take, yeah, maybe it's better I did it the other way, guys. It seems like it'll be a lot faster. 1 over, negative 1 I think it'll work. I mean, it'll give you, you should get the same answer. Barring any arithmetic error, you should get the same answer. Turns out the first way I did it seems to be a lot more straightforward. But for the sake of argument, I figure I'd show you the other way as well. So you're looking at this, you guys, and we got the answer. We got the answer we want. And that was I think it was problem number 31, wasn't it, guys? Yes. Let's see here. All right, there is problem 55, 56, and 58. Let's do those, and let's see how we can do this. For number 55, in deep space, two spheres, each of radius 5 meters, are connected by a 3.00 times 10 to the second meter length non-conducting cord. It is if a uniformly distributed charge of 35.0 millicoulombs resides on the surface of each sphere, calculate the tension in the core. All right, I wish they would have said more. They told us basically, guys, in deep space, two spheres, each of radius 5 meters, are connected by a 300 meter non-conducting cord. If a uniformly distributed charge of 35 millicoulombs resides on the surface of each sphere, calculate the tension in the cord. Here's one thing, guys. That's a pretty big radius for each one. Is the cord connected to the surfaces, or is it connected to the centers? That was my thing. My question on it, I guess you could say, that I had a little bit. I was, again, privy to the answer key on that, so I was able to work backward on that. I'll try to make the things reasonable for you guys when we are doing some of this stuff. This problem, this is just my opinion, of course, just my opinion. This problem should have been, I wrote it as well, this problem should have been more clearly stated. We are to assume that the cord is attached to each surface. The cord is attached to each surface. And that kind of changes the dynamic. Was it possible that there was somehow some connection non-conducting, and that was conducted to it was between the centers. So we're going to assume that the cord is attached to each surface, you guys. And so there's where you got to kind of watch out. Okay, so let's talk. So, the spheres themselves they'll behave as though they are pushing from their centers. Their uniformly distributed charge resides on the surface of each sphere, and according to Gauss's law, they are going to push as though all of that charge that they have is concentrated at the center. Sphere 1 and Sphere 2, for lack of a better way to name these, Sphere 1 will push as though all of its charge is centered at its geometric center. All of that charge is at the geometric center, or it'll act as though, it'll push as though it's at its geometric center. Sphere 2 does the same thing. So let's take a look here. Should be pretty straight. But again, watch out how they state something like this. But if the answer's already given to you the way I want them expressed, assume that the way they're talking is the language that they want you to be talking. From surface to surface, yes, but the distance between charges on average is from the center to the edge plus 300 plus from the edge to the center. Absolutely true. F equals, and they gave us the numbers. We'll repeat the numbers here. K is almost 9 times 10 to the 9th. It's 8.99 times 10 to the 9th. I know that they're 300 meters apart, surface to surface. Closest surface to closest surface. From the closest point, the closest part, from the closest, the surface closest to that, and the other one closest to the closest surface. Surface to surface, they're 300. I get that. But they do the electric force fields as though everything is concentrated at their geometric centers. And that's why you go 300 plus 5 plus 5. You do the mathematics. Force equals tension. And that's that. 56. A non-conducting thin plane sheet of charge carries a uniform charge per unit area of 5.20 microcoulombs per square meter. A, find the electric field at a distance 8.70 centimeters from the plate. B, explain whether your result changes as the distance from the sheet is varied. We've been there. We've been there, guys. We've already answered this one. All right, guys. Let's write it down. Let's talk about it. I think we're in pretty good shape. We did a lot of the heavy lifting earlier. It was with mathematics that we did not need for this particular course, non-calculus based physics. But like I said, some people already have that background. I wanted to kind of give you a look at it. Gives people something to think about. At the very least, you don't have to know it, but know the conclusion at least and some of the stuff we had said. What is it saying here, guys? Find the electric field at a distance of 8.7 centimeters from the plate. Sounds complicated. Not really. From the example that we already gave, from the example that the book gives us, we're fine. We know that. We concluded that earlier. Notice there is no, for this infinitely long, I don't know how they may have phrased it themselves here on this. The way they said it. I mean, whatever. They're kind of assuming, they didn't really say it, but they're assuming it's infinitely long or close to it, if that makes any sense, you guys. Close to it. It's very long. Thin, long sheet, and what's going on here? How do we look at this? There is nothing spoken of here. There is nothing spoken of here that pertains to the distance away from it. So it's not going to matter. We already answered B. We already answered B a long time ago, hours ago. What's going on here? Well, for this one right here, epsilon sub naught is 8.55 times 10 to the negative 12. Absolutely. The field, that's it. And we said it doesn't matter. That thing's infinitely long or close to infinitely long, and infinitely long, infinitely wide. If the dimensions are pretty much infinite or close to it for practical purposes, doesn't matter. The distance you are from the sheet. It's going to be the same E field. We proved it. We already proved that. So B, does it matter? Explain whether your result changes as the distance of the sheet is varied. B, the field does not vary with distance as long as the distance is small compared to as long as the distance is small compared to the dimensions of the sheet. Here's where it's close to infinite that they're talking about. I think the answer key goes along those lines when they say something like that. I'm quoting it. I've got quotation marks on there, so I'm sure it's from the answer key that I got that. And to their credit, that's true. The field does not vary with distance as long as the distance is small compared with the dimensions of the sheet. Okay, and you see that in my writing as well. 56, again, I guess I'm talking a little bit here. With this having been said, we will discuss this more in class from a strong intuitive standpoint. Okay. I hope we did already on film, you guys, right now as we've talked about. We can talk more when we're in class together as well. Okay. All right, fantastic, guys. We're doing great. That was 56. 58. 58, a small plastic ball. Again, it's the stuff I had circled early on in the in the discussion, you guys. 58, a small plastic ball of mass, m equals 2 grams, suspended by a string of length capital L equals 20 centimeters in a uniform electric field, as shown. If the ball is in equilibrium when the string makes an angle of theta equals 15 degrees, a 15-degree angle with the vertical as indicated, what is the net charge on the ball? It's basically the same argument that we've done in the past, you guys. Let's just do it again. Guys, it's essentially the same argument as last time, perhaps easier, you can say, in a lot of regards. There's a lot going on here. It's a lot going on. It's the same kind of stuff that was going on in the past, too, right? We said that there is a tension here, a tension component here, and a tension component there. A lot of ways to play it. This is important. If that's theta, these are parallel lines. This is a transversal that cuts those parallel lines. That's also theta. This is length L. This right here is Ty equals T cosine theta. It's not the way we're used to associating cosine. We associate cosine oftentimes with horizontal and sine with vertical, but you don't have to. Components are components. And this right here Tx T sine theta. Yeah, absolutely. There is going to be, well, I mean, we're looking at it. I mean, got this guy, you got this guy, and you got the whole thing here, and that's a tension. T for tension on that one, guys. Okay, so what do you want to say about it? We know that there is a pull down called the weight, mg, and it's equal to Ty. So Ty, the pull-up, is equal to the magnitude of mg. T cosine theta equals mg. T equals mg divided by the cosine of theta. You can jump right to here, guys. Absolutely. Well, this right here is 2 grams, which is 0.002 kilograms. This is 9.8. This is the cosine of 15 degrees. Remember, this is 15 degrees, this is 15 degrees. So you plug in the numbers here. Let's do it again. 2 grams is 0.002. 2 grams is 0.002 kilograms. This is 9.8 meters per second per second. This is the cosine of 15 degrees. Do all the mathematics. The tension in the string true. Now you want to know what the charge is on there, right? Well, let's talk. T sub x, see we know T, so T sub x ain't going to be hard to find, guys. T sub x and Fe are doing their own tug of war. Remember, guys, there's, we had this guy going down here, and we got this guy going over here. This is, best way to put it, I mean, what they're saying is here, this is the component of tension, and this is Fe. This is Fe, and this is the component of tension. So Tx and Fe are equal and opposite to each other, just like Ty and Mg down here. So Tx equals this. Tx equals QE. Tx is T. Yeah, looks pretty good to me. Solve for Q. The hardest part of this whole thing. The hardest part of it, right there. Get there. This is why it was good that we solved for T earlier. Plug in the value of T for which you solved. Go the sine of theta. Theta, we said, and again, I think I didn't even write it. It is written down in my notes, so I can't. There's sine of 15. It should be sine of 15, you guys. Cosine of 15 there. Right. Okay. Right. We already solved for T. Plug in the value of T for which you have an answer. I mean, here's the value of T. Right over there. Plug that in here. The sine of 15 degrees. Value of T times the sine of 15 degrees divided by E, and E is 1,000 newtons per coulomb. Did they have that? Let me just see, make sure. Yeah, right. They had 1.00 times 10 to the third newtons per coulomb. 1.00 times 10 to the third newtons per coulomb is 1,000. So T is 0.0203. Sine of 15 degrees, so T times sine of, 0.0203 times the sine of 15 degrees. Get an answer, divide that by 1,000, you got Q. Yeah, it was a positive it's a positive E field. For there to be repulsion in a positive E field, there's got to be a positive charge on it. Absolutely. And again, it was an E field. I mean, they didn't really specify positive or negative, but the very fact that they did not say, they didn't really specify positive or negative, but the very fact that they did not put a negative number on there means it must have been positive, because they got E equals a positive number. E equals 1.00 times 10 to the third newtons per coulomb. It's a positive number. So the charge on the ball has got to be positive. Otherwise, it would be otherwise it wouldn't go. That charged ball would not go in the direction of the E field. It would go opposite the direction of the E field. So it's a pretty significant point in its own regard to keep in mind. I mean, that's something legitimately could be asked. So that was 58. Let's go to the last two problems, 60 and 66, the last two problems. For problem number 60, the electrons in a particle beam each have a kinetic energy, capital K. Find the magnitude of the electric field that will stop these electrons in a distance d, expressing the answer symbolically in terms of capital K, E, and D. Should the electric field point in the direction of the motion of the electron, or should it point in the opposite direction? Let's answer that question first. If the electric field points in the direction of the electron, a positive test charge, would go toward the electron and then away. But a negative particle would go toward it. We don't want it to go toward it. We want the E field to point in the same direction. The E field, we want the E field to point in the same direction as the direction of motion of the electrons. In the same direction that the electrons are moving, you want the E field to point in the same direction, because a positive test charge in that E field would go in the same direction as the electrons are moving, but an electron would go in the opposite direction of the E field. And you want it to go in the opposite direction because you want to stop it. So it's got to be in the opposite direction. Okay, this is significantly easier than I thought it would be, the way they have it. Now, what I said is what I said, and it's correct. Let me say it again, and let me say some other stuff related to it, I guess you could say. Let's go to number 60. All right, guys, so the electrons in a particle beam each have a kinetic energy of K. That's each electron. Well, there's a lot of electrons. That's fine. We can assume that we can put together a big enough magnitude electric field to stop them. If the field is enough to stop any one of them, it'll stop all of them actually. If we're considering all of them if we're putting all of them under consideration. The electrons in a particle beam have a kinetic energy capital K. Find the magnitude of the electric field that will stop these electrons at a distance d, expressing the answer symbolically in terms of capital K, E, and D. Should the electric field point in the direction of motion of the electron, or should it point in the opposite direction? It should point in the opposite direction. We'll talk more about that. You want to change the kinetic energy, so each electron is moving like that, so we got to talk about that a little bit. Delta KE, in terms of magnitude, it was going this fast and you want to stop it. You want to bring it to zero. The total magnitude, let's not worry about positive or negative right now. For one electron, you want to take away that much kinetic energy. Q is the charge on an electron. Q is the charge on an electron. Well, let me put it another way. Yeah, Q is the charge on the electron, and that charge on the electron is called E. You want to take away all the kinetic energy. You want to take away all of the kinetic energy from a single electron. This is potentially a confusing matter. The problem solves really quickly, but you got to be really careful about it. Assuming you got an E field, and the E field is not going to get affected in any way, shape, or form. I don't want to get into all the particulars of this potential situation. The E field is what it is. There's an E field, and it's able to do something. Period. It's able to stop these electrons, no matter how many there are. Well, one electron has a kinetic energy of K. Okay, how many do n electrons? How much total kinetic energy is present if there's n electrons, each one with an average kinetic energy of capital K? Well, it's n times capital K, obviously. Okay, good enough. Let's just talk about one electron right now. You're going to take away K amount of kinetic energy. You're going to take away K amount of kinetic energy from one electron, from each electron. Really? Yeah, not only that, the force that you're going to give to each electron is Fe. You're going to apply it over a distance d, because you want to stop it over a distance d. And that means you took all the kinetic energy away. That means you did this much work, which is equal to the kinetic energy that you robbed it of. You robbed it of K amount of kinetic energy. What does that mean? You better do K amount of work stopping it. The E field is the brakes. And the brakes have to do the same amount of work that you want to rob from the electron. The same amount of energy. They have to do the same amount of work that you want to rob in terms of kinetic energy from the electron. Because that's the only thing under consideration right there. Q times E is the force. D is D, the distance, that's K. Q is small e. Yeah, that's it. That is the E field needed to stop one electron. How much of an E field is needed to stop n number of electrons? Well, you'd be doing n times the work. You know, this is why it works. Assuming you set there's still a lot of work. There's n times more work. If I want to stop n electrons, and that might be 1,000,000 electrons, you guys. Might be 1,000,000 electrons. N times k is the work I got to do. Wow. That's n times more than the force on one electron times d. Really? You know where I'm going. You know where I'm going. Solve for E. Look at it. The E field is certainly doing more work if you're stopping many, many more electrons. If you're stopping 1,000,000 times more electrons than you were earlier, you're doing 1,000,000 times more work. But the E field is still the same strength. It just means that the E field, well, that's great. That's a great point in its own right, right? I mean, that E field is doing a lot more work. It's doing a lot more work, but it's the same E field, my friends. Same thing. That was 60. Let's go to the last one, 66. Two small beads having positive charges, Q1 equals 3Q and Q2 equals Q. One of them, there's two small beads and they have positive charges. One of them has charge Q1, which is equal to 3Q. The other one is charge associated with it, Q sub 2, and that's equal to Q. One is 3Q and the other one is Q. One is 3 times more charge than the other, you guys. 3 times the charge is the other. 3Q is 3 times bigger than Q. So again, we got 3Q and we got Q. And they're fixed at opposite ends of a horizontal insulating rod of length D equals 1.50 meters. The bead with charge Q1 is at the origin, as shown in the figure. A small, let me see, you're right, as shown in the figure. A third small charged bead is free to slide on the rod. At what position X is the third bead in equilibrium? Do you understand that third bead, if there are two positive beads, you guys, opposite each other, that third bead could be negative, and there could be a tug of war between the two positive beads at the edges. It could be a negative one in the middle, and it can get to equilibrium. Or it could be a positive one in the middle, and it'll get to equilibrium. In fact, whether it's positive or negative, it'll be at the exact same location. It could be positive or it could be negative. The positive, there's going to be a pushing war, and they could be in the middle. The negative, be a pulling war, and it'll still be in the middle. As long as they're both positive at the outskirts. If the two outskirts are the same sign, both positive or both negative, the bead in the middle or somewhere between them, the bead somewhere in between them can be positive or it could be negative, and it'll still satisfy the criteria. Well, they're asking that question. You don't have to have anything else there. I said in this problem, sign will not matter here, and I just told you why. Let's take a look at it. I think we're in pretty good shape, guys. It should not be too bad. Now you heard the speech, guys, so probably don't need to deliver it again too much. I said in the notes, and you'll see the notes scrolling at the end of all this, sign will not matter here. Bead has charge, let's just call it capital Q. There will be the same force in both places. So what you got here is Q1, Q2. This guy's at the origin. So we get the distance right here. X is going to be the magic number we try to get. The whole distance is 1.5, and that's D. And that's D. And that's D. Let's figure it out. This is jet, like we said it. That's 3Q. This guy's Q. And I think we're good. Force is force. They got to be equal. They ain't going to be moving. It's either going to be an equal in tug of war if it's a negative bead, or an equal in the pushing war if it's a positive bead. If it's a positive bead, this guy pushes strong, and this guy pushes strong, and they push with the same strength, and nobody moves. If that's a positive bead, he pushes the positive. He also pushes the positive, and the pushing war is dead heat right here. If this is a negative, this guy pulls them, but this guy also pulls them. Same exact location, whether it's positive or negative. The mathematics holds on that. Force associated with electric fields are going to be equal. The Q1 guy, times big Q, that's going to be the bead. We don't know necessarily what that is. These are fixed really strong. They ain't going to move. Nobody's going to dislodge them. Absolutely true. I don't know. There's a lot we can say, I guess. Let's take a look at it. They are what they are. Let's see what we can say here. Let's make it. I don't know. Let me keep talking a little bit. Q1 is 3Q. That's the strong one. And that's capital Q. And that's x squared. KQ, Q, we got this. Divide by capital Q on each side. Divide by K on each side. Divide by small q on each side. Well, these don't cancel to nothing, guys. There's a 1 right here, and there's a 3 right there. I'm at the end of all that. It's 3 over x squared and we can, like I said, we can solve this rather abstractly without any definite numbers, any specific numbers put in there in terms of D, or we can actually, you know, like I said, we got a lot there that can actually get us there. So this is where it amounts to, guys. It comes right to here. I showed it slightly differently in my notes, but it's the same argument. It's a horse apiece, you guys. Didn't we say D was 1.5? Yeah, we did. Cross multiply. You know, you take this and yeah, we've been down this road before, right? I mean, you go 3 times the quantity. 3 times the quantity. 1.5 minus x squared, 1 times x squared. 3 is 3. Do all this. 2.25 minus 3x plus x squared. Multiply across here. We got 6.75 minus 9x plus 3x squared equals 1x squared. Unless I didn't make some sort of careless mistake, guys, this should be the way it looks. This is going to get you there. This is going to get you there. Now, you're going to get 2 solutions again, and it's just some things some things our common sense is going to tell us that we're not going to buy into, or at least that could happen, that we're just not going to buy into it. Perhaps there are 2 solutions that just seems inconceivable. The only thing that's going to work here is something, one unique something there. It's just not set up in such a way that you're going to get a double solution that is not unique. I mean, you could get, if the answer was 5, you get x equals 5, x equals 5, okay, something like, or whatever, or like right in the middle, or something like that, if that was the case. That would be the case if it was q and q, or 3q and 3q. It'd be right in the middle, and it'd be 0.75. You'd probably get a double solution there. X equals 0.75, x equals 0.75. Otherwise, that's not likely to happen, guys. So you look at it, we got our common sense, we're going to figure out where we're at on this thing. So we got to where we are. Let's do the quadratic formula. I mean, let's get these guys. You're looking at it, guys. Let me try to make some sense out of it, I guess. Let me add 1x squared on each side, and let me just rearrange things and figure out what I'm doing here. Let me add a 1x squared on each side. Minus 9x is plus a negative 9x. That's 2x squared. 2x squared plus negative 9x plus 6.75 equals 0. Ax squared plus bx plus c equals 0. You know a is 2. You know b is negative 9. And you know c is that. And how we actually did it. Well, that's fine. Let me stay with the way they got it, or the way I had this thing here. That's the opposite of b plus or minus the square root of the quantity. B squared minus 4ac over 2a. What does that mean? X equals the opposite of b. b is equal to -9. The opposite of -9 is 9. Plus or minus the square root of b squared. -9. The quantity -9 squared, not -81, but the quantity of -9 squared is positive 81, minus 4ac. 4, let's see how we can say this. 4ac. 4 times a is 8. 8 times 6.75. 8 times 6.75 is going to be 54. Over 2a. A is equal to 2. 2 times a is 4. X equals 9. Plus or minus the square root of. What's 81 minus 54? It's 27. This is 4. There's a lot of ways you can go here. 27 is 3 times 9. The square root of the product 3 times 9 is the square root of 9 times the square root of 3. That's 3 times the square root of 3. That's equal to x. X is equal to that. Yeah, it is. Let's not go too far with that. It's not going to be a double solution. One of them is going to be right. The other one's going to be absurd. The other one's not going to make any sense. It's got to be an answer bigger than it's got to be an answer bigger than half of 1.5. 1.5 is the whole length of the thing. You've got all this strong push from this, much stronger than what you got here. Much stronger than what you got there. Therefore, it's going to be skewed away from the center toward the smaller charge, towards Q. It's going to be bigger than 1.5. The way it looks is you get both answers there. You go for it. Let me just see here. You get one is 3.5. One of the answers, if you add it, if you take this guy right here and go 9, if you go, forget the negative here, the minus here. 9 plus 3 times the square root of 3, this is like 5.1. Let's say about 5. This is about 5. 9 plus 5. 9 plus 5 is 14. 14 divided by 4 is more than 3. Yeah, that's all well and good, but there's about no way that's going to happen. I mean, this whole thing is 1.5, so the 3.5, it comes out 3.549. That doesn't happen. With the minus, however, 9 minus about 5, that's about 4. 4 divided by 4 is about 1. It's about 9, actually it's 0.951. 0.951 was about 1. That's the one that works. So you got two scenarios, and I'm going to immediately cross this one out because it doesn't make sense based on our assumptions. Based on our preliminary assumptions, this is not acceptable. That's not acceptable. This is. On the plus side, it's going to be 3.5 something. On the minus side, it's going to be 0.951. And that one works. And that one works. This one does not. Got to throw it out. And that is it from chapter 15. That is it from chapter 15 from the Serway book. We'll proceed with chapter 16 the next time that we get together. Okay. Please wait for all the solutions from this. It'll look something like this. Hopefully I've got this centered right. Those 18 problems, the solutions for it are going to scroll at the end of this video. So thank you very much for your time. Take care.